Good afternoon, everyone. Welcome back to the Physics Colloquium. Today, we're very excited to have Professor Mike Bostock virtually visiting us from University of British Columbia. So Mike got his master's degree from Queen's University. Actually, I didn't get the bachelor's part, but master's degree from applied science from Queen's University, and then PhD from Australian National University in 1991. He then went on to do a postdoc at Utrecht, and then became a faculty member at UBC since 1993. I'm not going to list along all the awards and so on, but I'm just going to mention that Mike is a fellow of the AGU, so American Geophysical Union. He also delivered the 2010 Gutenberg Lecture, which is the seismology plenary lecture annually presented at the American Geophysical Union meeting. So he's really the pioneer, I think, for introducing scattering imaging to looking at structures underneath rays, especially back in the, I guess, early 2000s, taking advantage some of the deployments out in the West Coast, which is is talking about a lot more of the earthquakes there today. And his recent years, he's been kind of also working on the slow earthquakes, ETS, as you'll see today later, for the Cascadia and subduction zone. So without further ado, I'll let Mike take over the stage.
Well, thank you very much, Chinya, and thank you very much to the greater seminar committee for inviting me to come. I'm very happy to be here, and I've had some very nice conversations already. I'm going to talk a little bit about earthquakes in Cascadia, provide you with an introduction to the different kinds of earthquakes that we find in this region. I don't know how, I think most of you are probably familiar with the term Cascadia. It has, it's typically associated with the Pacific Northwest and southwestern British Columbia in terms of sociocultural trends, but it also turns out to be quite an apt descriptor as far as geophysics is concerned, which I will get into in a moment. So let me back off for a moment and just make some remarks about foundational theories in science. And in earth science, our scientific revolution took place relatively late in the game relative to our brethren in biology and physics. Most of you, I'm sure, are very well aware that in biology, biology experienced revolutions in scientific thought through Charles Darwin in the mid-1800s with his advancement of the theory of natural selection, and of course Watson and Crick with their discovery of DNA a century or so later. And of course in physics you've had revolutions at various times, notably classical mechanics with Isaac Newton, and of course the turn of the 19th century with the discoveries of quantum mechanics and general relativity, explaining phenomena at the very smallest and largest scales. Earth science, in contrast, had its revolution relatively late in the game. And that revolution came in the form of plate tectonics. And I suspect most of you, the majority of you, are aware of the very, very important role that University of Toronto played in that revolution. J. Tuzo Wilson was, of course, a member of the Department of Physics, and probably more than any other single individual is associated with the theory of plate tectonics. So we owe a lot to the University of Toronto and the physics department in that regard. So the theory of plate tectonics, most of you probably already aware to some degree.
Sorry, Mike, to interrupt, I don't think the slides are progressing. Is that?
Oh, dear. Well, that's interesting, isn't it? So does everyone see my desktop or the main window now, my keynote window?
No, I just see the earthquake in Cascadia. It's the title slide.
Okay, let's see here. I'm playing it again, and what you're saying is you do not see this picture of Charles Darwin and Isaac Newton. Okay. So let's see here. That's an issue. What do I need to do? I can try sharing my whole screen and see if that works.
Yeah, that might make a difference.
Now, can you tell me whether you see that?
Yes.
Yes, that looks better. Thank you.
Okay. Yeah, apologies for that. So this is the slide I was showing with some of the key figures, I guess, in revolutions in science. And as I mentioned, of course, biology and physics had their revolutions relatively early on in the game. The bottom portrait is that of J. Tuzo Wilson, really, as I mentioned, perhaps the most important single figure in the development of the theory of plate tectonics, which happened in the mid-1960s. So again, a faculty member at the University of Toronto, someone which is worth noting had both geological and physics training, and he combined those two skills in a way that positioned him to really lead the charge as far as plate tectonic theory. So the theory of plate tectonics posits that the Earth has a outer rigid shell, which Earth scientists term the lithosphere. The lithosphere is on average, say 100 kilometers thick in most places, and it overlies a more fluid substrate. When I say fluid, I'm talking about sort of long time scale behavior. The lithosphere, it turns out, is broken into about a dozen major plates, as we call them. And those plates are shown in this map. Hopefully everyone sees this now. The boundaries are shown in red. And the boundaries, of course, are where the plates move with respect to one another. And the boundaries are where we find earthquakes and other interesting phenomena like volcanoes. My focus is going to be on a little plate known as the Juan de Fuca plate. You can see the white arrow that points to it. And it's really sandwiched between the large Pacific plate and the North American plate. Okay, and this is the region that we call Cascadia. So Cascadia, in a geophysical sense, is defined by the interaction of this Juan de Fuca plate, which you can see sort of defined in terms of the warmer colors on the left, and the North American plate. Okay, and the Juan de Fuca plate, this area of the world is actually a very nice place to do geophysics because, as you can see, there are a range of different plate boundaries. The Juan de Fuca plate itself is defined by ridges on the western side, the Juan de Fuca ridge, for example, which is where oceanic plate is born, the Juan de Fuca plate and its sister plate, the Pacific plate to the west. So those are what we call spreading ridges. And we also have transform faults, numerous transform faults like the Nootka fault, for example, which you see labeled on that diagram, as well as what we call a subduction zone boundary. So that's the boundary just adjacent to the North American plate with the teeth on it. That's the symbol that geologists use to denote a thrust fault, okay? And as I say, Cascadia is really defined, the Cascadia subduction zone is really defined by the interaction of these two plates, the Juan de Fuca plate and the North American plate. The Juan de Fuca plate is sometimes broken into three components, the Juan de Fuca plate proper, which is the big central plate, and then two minor subplates, which are called the Explorer and the Gorda plates. But I'll generally refer to the composite as the Juan de Fuca plate. Now, the Juan de Fuca plate, as you can see, is born at the Juan de Fuca ridge and the Gorda ridge. And that means that it hasn't traveled very far by the time that it meets the so-called trench, which is that thrust fault that I mentioned, that plate boundary. And as a consequence, Cascadia is a very young and therefore warm subduction zone. In other words, the material that's going down is warmer than subduction zones in most parts of the world. The convergence rate is about 4 centimeters per year. That's roughly the speed at which your fingernails grow. And Cascadia has a lot of features which are typical of subduction zones, most notably a well-defined volcanic arc. So you can see on the right, arc volcanoes shown as those little red triangles. And many of you, I'm sure, have been to Vancouver. And when you fly into Vancouver from the east, you will often see Mount Baker looming on the close by. If you come in from the west, you may see Mount Garibaldi as you look up Howe Sound. And if it's a nice clear day and you look off in the distance, you'll also see Mount Rainier in the distance, which is that volcano at 48 degrees latitude. Just out, sorry, that's actually Glacier Peak. Rainier is a little further south, south of Seattle, sort of near Tacoma. Now, one of the interesting aspects of Cascadia is that it is seismically very quiet compared to most other subduction zones. And that's something that prompted a lot of interest early on, and we'll get to it in a moment. So my task today is really to try to introduce you to the main styles of earthquake or main styles of seismicity that occur in Cascadia. And I'm going to divide the zoo into 4 animals, if you like. Okay, there are 4 kinds of earthquakes that we're going to consider. And they're really ordered, I guess, in order of seismic hazard. So the first is the megathrust. And the megathrust, I don't have a cursor here, so I'll dispense with it. But that red bar that you see on the shallow part of the boundary between the Juan de Fuca plate and the overriding North American plate in this semi-cartoon cutaway, that is where the megathrust earthquake, the big one that you often hear referred to in the media, is going to occur. Okay, so relatively shallow depths on the boundary between the 2 plates. In addition, we have to worry about what we call crustal earthquakes. And those are earthquakes that are confined to the top 25 kilometers or so within the North American plate. Okay. The third class of earthquake is what we call INTRASLAB earthquakes. And those occur in the downgoing Juan de Fuca plate. So not on the boundary, but actually within the downgoing Juan de Fuca plate. Okay. And last and not least, because of enormous interest that's being generated in this new class of earthquake phenomena, I'm going to talk a little bit about what we call episodic tremor and slip, also sometimes referred to as slow earthquakes. And that's shown in the cyan bar. And that also occurs on the plate boundary, but it occurs a little bit down dip of where the megathrust earthquake will occur. Okay, so let's begin with the megathrust. So, as I've mentioned, Cascadia is seismically quiescent relative to other subduction zones. It doesn't mean we don't have earthquakes. We record earthquakes regularly, but by and large, not at the levels that you see in a place like Chile or Japan or New Zealand, for example. Okay, and in fact, in those early days, immediately after sort of the acceptance of plate tectonics, there was a great deal of debate centered on whether active convergence was actually taking place in Cascadia. There came in 1980, of course, about a decade after plate tectonics became widely accepted, there was emphatic affirmation of the active nature of our subduction zone in the form of the eruption at Mount St. Helens, which some of you may remember. Okay. But the question remained as to whether the subduction zone had recently sort of petered out, or whether there was likely to be still large earthquakes as we witness in other subduction zones. So this was very active debate, I guess, in the mid-1970s. And as much as anyone, really, Roy Heinemann at the Geological Survey of Canada was responsible for presenting the case, compiling evidence from various sources, and presenting the case that giant megathrust earthquakes actually occur off our shores. So I'd like to present to you some of the arguments that he compiled, not necessarily directly his work, but he compiled these arguments in a very compelling case to be made for the occurrence of large earthquakes off our coast. And I would say that the Americans were the holdouts here. They were the ones promoting the notion that Cascadia was sort of either it was a dead zone as far as earthquakes are concerned, or that convergence was happening so steadily that that large earthquakes wouldn't occur. In other words, there was sort of a steady creep going on as opposed to episodic violent events. So to move along, I guess it's first worthwhile recounting a few notes concerning what we call the megathrust earthquake cycle. So what you see on the left is a couple of cartoons. The upper cartoon reflects what's going on during what we call the interseismic period. So in the interseismic period between large megathrust events, we have an oceanic plate, which is of course subducting beneath the North American, in this case, the North American plate. So the oceanic plate is the Juan de Fuca plate. It is subducting beneath the North American plate, and the two plates are locked at shallow depths. So along their boundary at shallow depths, there is a portion that is locked, okay, due to friction. And as a result of the fact that the oceanic plate is moving downwards, there is deformation accruing in the overriding plate that you can see in the form of uplift in various locations, down warping in other locations near the trench, as you can see, and an overall shortening in the plate. Okay, and as I mentioned, Juan de Fuca plate converges at about 4 centimeters per year with the North American plate. And as I'll get into in a moment, the recurrence interval between big events is about 500, actually closer to 550 years. So if you do the math, you'll note that over 500-year period between big events, we've got 20 meters of displacement basically contributing to deformation, that uplift and shortening that you see in the overriding plate. When a great earthquake happens, basically all of that elastic deformation that is stored up in the overriding plate is released in the matter of a few minutes. Okay, and of course this gives rise to a variety of catastrophic phenomena, and most notably tsunami inundation, and of course large shaking as a result of the waves that are produced. We'll talk a little bit about how we calculate the actual size of earthquakes in a moment. And what Roy Hyndman proposed was that Cascadia was subject to this same kind of megathrust earthquake cycle. So let's take a look at some of the evidence that he compiled based on the work of others to make this case. So as I sort of emphasized in that last cartoon, there are portions of the North American plate that through the earthquake cycle should be going up and portions that should be going down. And by and large, along the coast, we're in that region where uplift is occurring. And what that suggests, given the fact that great earthquakes involve a very sudden release of elastically stored energy, we anticipate there are going to be, as a result of large earthquakes, there are going to be very rapid changes in the elevation of the shorelines, okay? And because these shorelines are subject to inundation by tsunamis, and tsunamis are highly energetic phenomena, they carry different sediment loads than sort of standard sedimentation deposition in coastal marshes, okay? And this led Brian Atwater, a geologist at the University of Washington, to suggest that one way of looking at evidence, what we call paleoseismic evidence for past earthquakes, would be to dig into coastal marshes. And when they did that, they unveiled what they call a stratigraphy that you see in the left-hand figure, where you've got a range of different layering. In particular, there is sort of normal marsh deposits interspersed with sand layers that we can identify with tsunami deposits. And it turns out that if you dig down into the marsh, there's sort of a regular repetition of this sort of layering. Regular marsh sediments interspersed with these peculiar sand layers, okay? And the youngest of these sand layers, there's organic material associated with that. In fact, part of the clues associated with these marshes is that there are old trees that are still standing in these marshes that were killed centuries ago. And the radiocarbon dating of some of this organic material laid down, for example, in the tsunami sand layers, indicates that the last major tsunami appears to have occurred somewhere in the last 300 years, plus or minus a few decades. Okay, so this was one piece of evidence suggesting that there had been at least several megathrust earthquakes in our recent geologic past. So another piece of paleoseismic evidence which entered the story was actually work done again by a Canadian, well, not a Canadian, he's actually a New Zealander, but he's worked his, he's probably a Canadian now, he's worked his career at the Geological Survey of Canada again, just like Roy Hyndman. But John Adams is a geophysicist at the Geological Survey of Canada in Ottawa, and he had the idea that by looking at what we call turbidite deposits one might gain further information into the history of earthquakes on our coast. And so these turbidites are basically underwater landslides. And as many of you will appreciate, the west coast of North America, there are several large rivers, for example, the Fraser River in the lower mainland of BC, as well as the Columbia River near Portland. They deposit dense loads of sediment on the continental shelf. And of course, there's generally large levels of erosion, of course, along the Coast Range in Pacific Northwest. So there's a fair sediment input, and they rest on the shelf. And Adams proposed that, in large earthquakes, one might anticipate that the shaking due to those earthquakes would cause submarine landslides. And he put together a very compelling case by looking at these turbidite deposits in various locations off the coast of the Pacific Northwest that, in fact, deposits in these various canyons on the West Coast all showed evidence for synchronous landslides. And for this to happen over hundreds of kilometers of a long strike distance really suggested that we had very large events that were triggering these landslides simultaneously up and down the margin. And as I say, put together a very strong case that has since been taken on by others. And we have now quite a detailed picture of great earthquake occurrence back right up until about the end of the glacial period, so 10,000 years ago or so. And you'll see the time scale on the right, that cartoon that shows sort of the regular occurrence of these events. And you'll notice also down near the 13th event, there is a very important, there is ash in some of these turbidite deposits that allow one to date those deposits at something like 7,770 years ago, and allows us to provide, basically to assign a meaningful timescale to the entire suite of events. And from that, we see that these large events occur at a recurrence interval of about 550 years, but that there is a fairly large standard deviation associated with them of about 200 years ago. So that's that very important part of the detective story in terms of understanding the incidence of large earthquakes off the coast. Now, if we want greater precision, we need to access the very extensive and detailed geophysical logs of the Japanese, who have recorded, for example, tide levels back for at least the last millennium. Okay, and in fact, researchers have done this, and they noted that basically back in the year 1700, on the dates of January 27th and 28th, very large tidal waves in excess of 2 to 3 meters in height, in excess of sort of normal levels, were recorded. And there was no explanation in terms of local earthquakes in the region. And so most of us now believe that the most likely date of the tsunami, which occurred, which was initiated off the west coast of North America, that last major megathrust earthquake, actually occurred on accounting for the time of flight, if you like, of tsunami across the Pacific Basin, that it actually occurred at 9:30 p.m. on January 26th of the year 1700. Okay, so we actually have fairly good precision on the actual timing of that event based on this extra information from the Japanese tidal records. And this is supported by additional information, notably accounts of indigenous peoples of what they refer to as the Great Drowning. So it's gone down in folklore of the indigenous peoples that, many generations ago, there was a major event that basically wiped out coastal villages. And so all of these pieces of the puzzle sort of fit together. So these days, of course, we can test the notion that there is strain buildup in the overriding plate through modern instrumentation. And so we use highly precise GPS instruments, similar to those that you find in your phone, but of course they need to be very carefully calibrated, thermally shielded to measure the very small signals that are the result of Earth deformation. And I'll talk a little bit more about these measurements in due course. But you can see in the map in the bottom right, you can see the GPS velocity measurements at 3 GPS stations on Vancouver Island. Stations at Ucluelet on the coast, Nanaimo on the inland coast of Vancouver Island, and Albert Head, which is just south of Victoria. And you'll notice that those stations are moving in a northeastward direction at roughly a centimeter per year. Okay, so they are testament to the notion that this, that there is a locked zone between which the two plates are locked, and deformation is accruing in the overriding plate. Okay, let me say a few words about earthquake magnitude. I know many of you have probably heard the term, and it is a logarithmic scale. So it's a logarithmic scale, and it's a logarithmic scale really, I guess, largely for public consumption. It's a way of quantifying the size of an earthquake on a simple scale that ranges typically between about 0 and 10, that is easy for people to digest. And it's based on a more fundamental physical quantity, which is known as the seismic moment, which is a proper physical characterization of the size of an earthquake. And the seismic moment is given by the formula that I have listed, and it's a product of 3 factors. It's a product of the strength of the rock, as measured through its rigidity or shear modulus, mu, times the area of the fault that ruptures, times the average slip over that area. Okay, and as I'll show in a moment, a magnitude 9 earthquake involves large, needless to say, large quantities as far as area and slip are concerned. So about 20 meters of slip, that's sort of the slip budget that we have based on 500 years of accumulated displacement at 4 centimeters per year, and an area of about 100,000 square kilometers involved. So I'll show you that in a moment. But let me say that these large earthquakes, which, magnitude 9 earthquakes probably occur once every 5 to 10 years or so, they are responsible for the vast majority of the seismic budget of the planet. So all those small earthquakes we hear reported on, even the magnitude 6s and so on, they are nothing like the energy release of a large magnitude 9 earthquake. Okay, so how do we come about quantifying the magnitude of a Cascadia event? And it's really that simple. It's the formula that I gave you. So the rigidity of rock doesn't vary a lot. It's on the order of 30 gigapascals or so, typically. The area of rupture is known as the locked zone. Okay, I've referred to it already. It's the zone where the 2 plates are locked. And the locked zone we can determine through a variety of means, but GPS is certainly an important factor. You can imagine that being able to define the regions where North American crust is going up versus going down provides fairly tight limits on where the down dip limit of locking is, for example. And the general consensus is that the locked zone is defined more or less by the green region that you see plotted on the map. Okay, that zone is on average something like 150 kilometers in width, and we're extending from about 40 degrees latitude up to about 50 degrees latitude. So we've got about 1,000 kilometers worth of a long strike distance. And so the math works out. Basically 20 meters times that area gives rise to that area. And of course 30 gigapascals for typical rock strength gives rise to that magnitude 9 figure. Okay. Just to further emphasize that fact, this is a plot of what you see on the left is a plot of the area of rupture of the Indonesian earthquake that struck December 26, 2004. I'm sure many of you will remember waking up on that Boxing Day to news of that horrifying tsunami that devastated much of the Indian Ocean basin. And the The rupture area of that earthquake is shown in the black outline, and you'll notice that it corresponds reasonably well to the area that we anticipate will rupture in a megathrust event, or that could rupture in a megathrust event off our coast. So similar areas, and we have every reason to expect similar ground shaking and similar tsunami generation. Okay, so what are we doing to help prepare for this, what seems like an imminent eventuality? There's a fair amount of work being undertaken these days towards what we call earthquake early warning, or EEW, and Canada is involved in a partnership with the United States on that front as far as Cascadia is concerned, and that involves these cabled observatories, underwater cabled observatories. The Canadian one is run by Ocean Networks Canada, where this slide comes from, and our observatory is basically, the center of control is Port Alberni, and it comes out that the long fjord at Port Alberni, and then makes its way out across the Juan de Fuca Plate, around to the ridge, and then back in. And this is an earlier figure. There are now many sensors distributed about that cabled observatory. And what's important, particularly important, is those sensors that are close to the thrust fault. And you can see that thrust fault, again, the geologists use that signature with the tooth marks pointing inward toward North America to denote a thrust fault, and that's the location of the so-called trench. It's not a well-pronounced trench the way that you see in other subduction zones, because there's so much sediment coming off the coast that the trench, the actual valley that you would see there, is filled with sediments. But those sensors are there and in close proximity to the trench, because when the earthquake begins, those sensors will pick up the first signals. Okay, and we have algorithms that that are constantly looking at these signals in real time, and when the algorithms tell us that there is a shaking afoot, those signals, those calculations, of course, are done in terms of the speeds of electrons, and those recordings provide us with necessary preliminary information to alert people by cell phones, alert emergency preparedness people, utilities, and so on, of the imminent danger that is likely to occur within matters of tens of seconds to minutes. Okay, the whole early warning system works on a sort of thunder and lightning analogy. On the East Coast, you guys, of course, are in eastern parts of the country, you experience more thunderstorms than we do, and as a young child, of course, you're often taught that when you see lightning, and of course you wait for a few seconds, and you'll hear the thunder following, and of course the precise time interval between lightning and thunder tells you something about how far distant the lightning struck. And of course, what we have working in our favor in this regard is that we've got weaker, faster waves, known as compressional waves, that alert us to the shaking, and the damaging waves, or what we call shear waves and surface waves, they arrive after the compressional waves. So that provides us this additional sort of advance warning of the big shaking. So these sensors are in place. This is a picture of one of the Neptune or Ocean Networks Canada seismometers on the seafloor. There's a seismogram, a nominal seismogram that shows you the weak P arrival, compressional arrival, arriving before the stronger S arrival, which tends to cause the main damage. Okay, so early warning systems are already in place in Japan and Mexico, and have provide both individuals and utilities and so on with necessary important advance warning of imminent shaking. So one of the efforts we're engaged in these days, and early warning should come to our shores. All the testing is going on at the present time, and I expect there'll be apps available to the general public in the space of a year or so. Okay, a little summary about the megathrust. So there's compelling evidence, as I hope I've demonstrated, that indicates that we've experienced regular events off our coast for at least the last 1,000 years at intervals of about 550 years, plus or minus 170 years. There's very good evidence that the last event struck on January 26, 1700. And when you consider the recurrence interval with the standard deviation on that mean, then you know we have to start preparing right away, because there certainly have been intervals as short as 300 years in the past. Okay, so we can anticipate a magnitude 9 event on this boundary, and as I say, there are efforts to help mitigate the hazard posed by the megathrust. So let me move on now to the topic of crustal earthquakes. So these pose another risk to denizens of the Pacific Northwest. They occur in the overriding crust, as I've mentioned before. It turns out that Canada's most damaging earthquake struck, at least since European settlement, struck central Vancouver Island in 1946. And thankfully, there were very few casualties, I think only 2. But shaking was widespread. It was felt as far south as Olympia in Washington. There was a lot of damage to masonry and so on. I think 75% of chimneys in the Courtenay-Comox region collapsed on roofs and so on. So a lot of damage. One of the enduring enigmas is we still don't have a good sense of what fault gave rise to that earthquake. There's a leading candidate known as the Beaufort Range Fault that runs along the spine of Vancouver Island, but there's no seismicity on that fault currently. So it's still very much an open question. Another fault that is of great concern to denizens of the Pacific Northwest is the Seattle Fault. And the Seattle Fault is aptly named because it actually runs through downtown Seattle. Okay. In the lower map figure, you can see a map of Puget Sound. And that feature that runs east-west, the red boundary, if you like, is the Seattle Fault. It runs from the Kitsap Peninsula through downtown Seattle. And it's a major concern, not least because Seattle, as many of you may know, is situated on top of a sedimentary basin. And the low density and low rigidity of sediments means that ground motions are amplified. So there is some evidence from paleoseismic studies, trenches and so on, that the Seattle Fault ruptured just over 1,000 years ago in a magnitude 7 earthquake. So similar to that Vancouver Island earthquake, it is one of these seismogenic structures that occur in our region. It's probably Seattle's most serious earthquake threat because of its proximity. Okay. This is by no means the only fault. I've already mentioned the Beaufort Range Fault on Vancouver Island, and I'll come back to Vancouver Island in a moment. But the Americans have mapped extensive fault network through the Puget Sound region. Okay, you'll see a lot of them here. TF you'll see it further south in Puget Sound. That's the Tacoma Fault Zone that puts residents of Tacoma at risk. If you look up to the north, you'll notice a fault labeled DMF. That's the Devil's Mountain Fault Zone. And it extends from, you can see sort of eastward parts of Washington through past Whidbey Island, and it's making a beeline for Victoria, as you can see. And so that's a concern, and that's prompted people to look carefully at Vancouver Island. And this is very recent work by researchers there, Kristen Morell leading a group of people from UVic and collaborators. And it appears that the Devil's Mountain Fault that you see as DDMF in this particular figure in the upper right is contiguous with the Leech River Fault, LRF, okay? And that runs right by downtown Victoria, okay? And there's been a fairly extensive paleoseismic work. I'll show you a figure in the next slide that where basically paleoseismologists go and dig trenches like they did on coastal marshes into the surface traces of these faults and try to look for evidence of past earthquakes and date them and so on. Okay, the Leech River Fault runs in close proximity to several hydroelectric dams and the Sook Lake Dam. that supply power and water to Victoria. So this is indeed very serious as far as Victoria is concerned. And in fact, the trenching suggests that there have been at least 2 magnitude 6 to 7 earthquakes in the past 15,000 years. So LIDAR is a very important tool in this regard, and is something that is now being used increasingly on Vancouver Island to try to help see through the dense vegetation and identify fault scarps, including the Beaufort Range, which I mentioned a moment ago. This is a figure of, you can see the arrows pointing to the scarp of the Leech River Fault, where they've done the trenching along 2 profiles, P1 and P2, and some of the evidence for throws along that fault, which gives rise to these predictions of, or these the evidence for past earthquakes on the fault. So let me just summarize the crustal situation, the crustal earthquake situation, by saying that, these are a very serious concern because they can occur anywhere in the North American crust. They're not limited spatially, and in many instances, they may be blind. For example, over most of its extent, the Seattle Fault is obscured by either sediment cover, water, or vegetation. And so one has to do very careful geologic, paleoseismic detective work, sleuthing, making use of other technologies like LIDAR and so on to identify prospective scarps and then go and do the forensics, okay? They can involve magnitudes up to 7.5, so a good deal smaller than the magnitude 9, but remember, if they run by a population center like Victoria or Seattle, or for that matter, Vancouver, then they are capable of generating just as much damage as a magnitude 9 earthquake. The recurrence rates are low, which is a good thing, of course, but makes these things harder to identify. All right, so let's move on to the 3rd class of earthquake. And that is, that earthquake, as I mentioned, is known as intraslab seismicity or intraslab earthquakes, and they occur within the downgoing oceanic plate, the Juan de Fuca plate. So one of the typical features of subduction zones, and one which, an observation which was a major piece of evidence in assembling the theory of plate tectonics, is the presence of what we call WADATI BENIOFF zones. And those are dipping planar features defined by earthquakes that plunge deep into the mantle, in some instances down to 600 kilometers or so. And the figure you see on the left is a cross section through across Honshu, where the Pacific plate subducts beneath the Eurasian plate. And you can see in red dots, the shallow earthquakes, and in green dots and blue dots, the deeper, what they call WADATI BENIOFF zone earthquakes associated with the subducting plate. So the subducting plate is cold, and because of the physics of conduction, it means that heat dissipates much more slowly than subduction proceeds. And the plate stays cold for quite some time as it sinks into the mantle and can sustain brittle failure. The details of that, of brittle failure at confining pressures corresponding to hundreds of kilometers, still something that seismologists and earthquake scientists are working on. But basically, it's, I think we all do agree that it's the cold nature of the slab that gives rise to the condition, that presents the conditions that allow brittle failure to occur. So one additional notion is it also seems that these earthquakes are associated with phase transformations in rocks. Phase transformations, for example, everyone's familiar, I think, with carbon going to diamond. We're looking at solid-solid phase transformations in this instance as well. And these earthquakes can actually get very large. The very largest can even exceed magnitude 8 on occasion, but that's very, very rare. The majority of large earthquakes occurring in slabs tend to be on the order of magnitude 7 or so. And as I mentioned, they're thought to be enabled in part through metamorphic reactions, phase transformations. And many of you will have heard of the term basalt. Basalt is, of course, the major rock type of oceanic crust. And of course, oceanic crust is getting dragged down in these subduction zones. And when you take oceanic crust or basalt down below, say depths of about 50 kilometers or pressures corresponding to depths of 50 kilometers, it undergoes a solid, the minerals therein undergo solid phase transformation, transforming to another rock type known as eclogite. And along with that reaction comes the release of water. And there tends to be a fair amount of water in the subducting plate because, of course, it's spent much of its history on the, as part of the ocean floor. And so water inevitably gets into the plate and in particular, the upper portions of the plate. And water, although I won't get into the details, water probably plays a very, very important role in terms of enabling these earthquakes to occur by lowering effective stresses and elevating pore pressures. So these are two models of BENIOFF zones in Honshu, again, Northeast Japan, and Vancouver Island for contrast. And you can see the earthquakes plotted in both cases as sort of black dots. And you'll notice there's a great deal more activity in Honshu than there is across Vancouver Island. You see the CRUSTAL earthquakes in the top 30 kilometers in Vancouver Island. So those are the events that I just spoke about. And if you look carefully, paralleling the subducting Juan de Fuca plate, it's sort of shown in those layers of green, yellow, and red, you'll see black dots that refer to earthquakes in the subducting Juan de Fuca plate. So these are the INTRASLAB earthquakes I'm talking about. Far fewer earthquakes than are present in the Pacific plate at Honshu. And this, when I talk about the quiescence or the relative seismic quiescence of Cascadia, this is what we're talking about, far fewer earthquakes. Nonetheless, they do exist. And we think that the quiescence is in part due to the general warmth of the slab. In fact, slab earthquakes don't occur everywhere in Cascadia. They occur primarily in the southern Vancouver Island and Puget Sound regions, as it turns out. Okay, one thing I should mention is that large events are possible, and in fact, they have occurred. So I don't know if any of you were perchance in the Vancouver region as part of holidays, for example, in 2015, December 30th, just prior to New Year. We all experienced here a magnitude 4.7 INTRASLAB event. This was below, I think, Saturna Island. That woke a lot of us up. It occurred around, I think, 11 o'clock. So some of us had gone to bed already. And I remember the shaking, feeling the P wave and followed by the S wave from that particular event. Damage from earthquakes tends to sort of set in at around magnitude 5. So there was very minor damage from this 4.7 earthquake, just very local damage. I think perhaps a few shattered windows and so on in the Gulf Islands, but nothing major. So that's an example of an INTRASLAB earthquake. As the National Post headline reads, it was no megathrust, no big one, but it was a moderate BC earthquake. I guess 14 years prior to that, another earthquake that I experienced occurred in Nisqually, which is a little town just near Tacoma, I guess, just south of Seattle. And that was a magnitude 6.8 earthquake. So getting up to sort of those maximum anticipated magnitudes. And that is very clearly in the danger range and caused a lot of damage, as the headline indicates, billions of dollars. It came rolling through Vancouver. I remember feeling the rolling. I had time to get underneath my desk and protect myself. Thankfully, there was no damage in our neck of the woods, but there was quite considerable damage in Seattle. So that earthquake occurred at a depth of 52 kilometers beneath Olympia, or more properly Nisqually, magnitude 6.8. Seismologists sometimes use an intensity scale, which is more a measure of damage than it is of earthquake size, but this was magnitude or intensity 8 on that particular scale. And that it provides engineers with a good indication of the level of damage. Very fortunate that there was only one casualty. It was indirect. It was more the result of a heart attack, but there were plenty of injuries as a result of that particular earthquake. So lots of damage incurred in Seattle. So this is a map of intraslab earthquakes in general. And there's lots of small earthquakes occurring offshore and off the west coast of Vancouver Island within the subducting slab. By and large, those are quite small. It's the earthquakes that you see through the Puget Sound region and even up into Vancouver that are more of a concern, because for obvious reasons, those earthquakes are occurring directly beneath urban centers. And if you get magnitude 6s and 7s, they have a very short way to go to Seattle, Victoria, or Vancouver. Now, the good news, if it can be called good news, is that at least on the Canadian side, those events tend to be quite a bit smaller. In fact, around Vancouver, the deep earthquakes are rarely exceed magnitude 2. And there are a few, if you know the Vancouver area, well, those easternmost earthquakes are up the Fraser Valley. Those are about 100 kilometers depth, but they're tiny. In contrast, the southern Puget Sound around Seattle, that's experienced 3 magnitude 6.5 and above earthquakes in the last, I guess, 60 years or so, including the Nisqually earthquake that I just spoke about. So for one reason or another that we don't quite understand, Seattle seems more prone to these earthquakes than we do north of the border. There have been magnitude 5s in the Gulf Islands, Saturna-Pender region, which are just at the sort of damage threshold. And if you look carefully, my cursor isn't active, but if those of you who know Texada Island, if you look just south of Texada Island, or if you look west from Vancouver, there's a cluster of events close together. And we've mapped that structure. That's at 60 or 70 kilometers depth. And those earthquakes form a nice planar structure, suggesting that there's a fault there. If it were to rupture in its entirety, it would certainly give rise to a magnitude 6 earthquake. But thus far, there's been nothing but little magnitude 2s and 1 or 2 3s. So we're not sure about what the potential consequences are of that particular structure. But certainly something that we need to be concerned with. So let me spend the last few minutes, and I hope I'm perhaps a little bit running a little bit over time, but I'll try to go through this quickly. This is one of the fascinating elements of earthquake science that has opened up in the last few years, and this is this notion of slow earthquakes, and it was really discovered on our shores, as I'll point out. So. As I've mentioned, the Juan de Fuca and North American plates are locked along the megathrust boundary, that locked zone that I pointed to earlier. GPS stations provide us with an indication of ongoing deformation. We know a lot now about recurrence intervals of large earthquakes and so on. In the figure on the left, you can see again these GPS estimates of velocity at various stations, and all those arrows are pointing to the northeast, indicating shortening is occurring in the Vancouver Island Lower Mainland region. These are examples of the time series of those GPS measurements. Okay, so those velocity vectors reflect these particular measurements, and you can see they are records of motion at Station Ucluelet on the west coast of Vancouver Island. The top left figure shows the motion in the north direction over about, I guess, 4 years or so of recording. And you can see there's a steady movement in the positive north direction. If you look at the figure below, there's a steady movement in the east direction. So it's all pointing to that northeasterly direction. And there's a slight, on the right-hand side, you'll see the vertical component. And vertical component is always noisier than the horizontal components for reasons I won't get into. But there's a small down warping signal there. Okay, small decline in the elevation of Ucluelet. So Herb Draggart and his colleagues at the Geological Survey of Canada made a very interesting discovery around the year 2000. They were looking at the signals from the newly installed GPS network, and they noticed that I think this is the station at Albert Head, they noticed that along with that sort of north and easterly progression, that the station Albert Head exhibited for a very brief period of time a slight reversal in its motion, which you can see by that change in that brief change in slope on both of those two plots. Okay, indicating that for a brief moment, or a brief period of time, I should say, the station moved, instead of going from north to east, it moved from south to west. Okay. Now, initially, this was sort of, initial thought was that this was some kind of artifact. Perhaps there was a bear resting on the station, or perhaps the monument had become insecured in some way or another. But when Draggart and his colleagues went around and looked at signals from other nearby GPS sites, by and large, they all showed a similar little jump, if you like, in the time series. Okay. So Ucluelet, you see on the left, and Nia Bay, that's in Washington. The two stations, Holbrook and PABH, are outside. They're at long distances away from Vancouver Island, so you don't have to worry about those. Nanaimo, NANO, PGC, Albert Head, those are all sort of on central Vancouver Island. And then the landward stations at Whistler, WSLR, they don't show much sign of it. Okay, Chilliwack is CHWK, the signal is gone. But on those Vancouver Island signals, you can systematically see that little change in direction. So this is a plot again of the secular motions. The black arrows are those velocity vectors I mentioned a moment ago. And then the red arrows pointing in the opposite direction are the displacement due to that little reversal. Okay, that's about 4 millimeters of reversal during that little episode. Okay, and as you can see, the red arrows point in approximately the opposite direction from the black arrows. Okay, so this was a distributed event, and it was probably localized to the region shown by the arrows. Okay, doesn't extend up and down the entire subduction zone. It was principally in the sort of Puget Sound, Vancouver Island region. So when Draggart and his colleagues went to look at this more carefully, they noticed that this reversal took place over a period of just under 2 weeks or so. Okay, and it implies displacements on the order of a centimeter at depth. Okay, and remembering that formula that I showed you for seismic moment, that is displacement times area times rigidity, strength of rock. You turn that into a magnitude. That's a magnitude 6 to 7 earthquake. And yet no one felt a thing, only sort of measurable in these very, very finely tuned GPS instruments. So this is, of course, no one felt a thing because this energy was released rather than over a period of seconds. It was released over a period of a couple of weeks or so. Okay, and that period, that's simply too long a duration to generate significant seismic waves. Okay, so this is the reason why we call these things slow earthquakes. Okay, Draggart and his colleague Gary Rogers, went back into the GPS records that extended back to the early 1990s, and what they found, added to the interest in this story. You can see this is the record of GPS motions again on, I guess, Albert Head, I believe. The green line that you see on the graph is sort of the secular trend representing sort of the buildup of deformation on that locked portion of the megathrust. And yet at regular intervals, 14 months plus or minus 2 months, that little red line defines the sawtooth signature of these slow earthquake events. So these slow earthquakes occur at regular intervals, and the modeling indicates that they have an origin down dip of the locked zone. So down dip along the plate boundary, but down dip of where the megathrust will occur. Okay, so this is a cartoon. The upper figure sort of provides you with a perspective from the northeast of the top of the subducting plate. And the locked zone is that portion of the plate that's sort of shaded in greens into the transition region of sort of light yellowish green. And the slip that these measurements are manifesting is occurring at deeper levels. So down between 30 and 45 kilometers or so depth. In the very bottommost figure is a cross section, again showing the subducting Juan de Fuca plate and the overriding North American plate. And that yellow dashed line is where the megathrust is anticipated to strike. And the slow earthquake is relieving stress at deeper portions of the earthquake. Presumably farther down dip, the slip is being accommodated in a very steady gradual slip, and the slow earthquakes represent sort of an intermediate mechanism of fault deformation. Okay, This has excited a lot of interest in earthquake science because it represents a new class of fault rupture, not one that poses any immediate or direct danger or consequence, but there's a lot of interest in the potential use of these slow earthquakes in terms of getting a better handle of what's going on updip in the megathrust. And so I liken this to a frayed rope. So in other words, we're releasing stress at down dip portions of the plate, and presumably that's ratcheting stress in the up dip portions. It's a little bit like a fraying rope where every time a strand breaks, you know, the stresses are transferred to the remaining strands and increased. And so I think many people have begun looking at the possibility that these, you know, that large earthquakes may occur preferentially during a period, you know, one of these 2-week periods when slow earthquakes occur because of this ratcheting effect. So lots of fodder there for earthquake science, lots of people working on these problems. And I think I've probably gone past my time. I apologize for that. But let me summarize by just saying that British Columbians live on an active plate boundary. The case was made in the 1970s, soon after plate tectonics, that this is a perilous and dangerous place to live. Cascadia is disquietingly seismically quiet, but the seismic hazard is high. And so the hazard includes not just the main megathrust event that everyone talks about in the media, but also these smaller but closer earthquakes that occur in the continental crust and the subducting plate. And there's a lot of effort these days in terms of trying to mitigate the effects of eventual earthquakes through early warning systems and, of course, improved monitoring that is improving our understanding and resilience to seismic hazards. So thanks very much. Apologies for going over time, and I'm happy to entertain any questions.